Thank you everyone for joining this session. My name is Rocky. I am having 14 years of experience. I work with Adobe as an architect, and I love to share content on LinkedIn. I'm passionate about technologies, and I keep on sharing content on LinkedIn. So today, in today's talk, I'm gonna share the journey of processing massive amount of information. First, I will share the overview of the system that we have, what was the problem, and then when we thought of a design, what were the different points that we had to consider. Then I'll talk about the platform which we choose and why we chose it. And then I'll talk about the technological landscape that we have, high-level architecture, and then once we had that system live, then what are the different problems that we face and how we overcame those problems in terms of how we ensured that data quality should be in place, how we ensure that system is running fine. And since we were running this system, since we are running on this system in cloud, how we are making sure of a cost in terms of storage, because we process massive amount of information, how we are making sure that compute that we use is optimized using ML or other best practices. So this is the journey I'm gonna share in this talk. So this is the overview of the system. So we started in 2018 when some of the internal teams reached to our group. I work with a group, IDS, Information Data and Services in Adobe. So our group deals with all the data of Adobe, be it finance, be it CRM, customer-centric, event, product usage, anything, whatever comes or goes within Adobe or through customer, it comes to our group. So in 2018, so there were few teams which reached to us, product teams and marketing teams. They wanted to use the product usage data from ETS. ETS is our event tracking system, which basically tracks a lot of event. So when, let's say, event like when a user has signed up, so an event would be triggered like create user. A user has downloaded a Photoshop product, an event would be triggered. User has converted from trial to paid, an event will be triggered. If a user is doing some installation and an installation got failed, that event would be triggered. Similarly, there are around 1,000+ different events that gets triggered when user performs some action. User has purchased something and user has launched a product. So a different event will be occurred, and that will be captured through event tracking system. So they wanted a system where they could use such kind of event. But when we started, the volume was in couple of million, and we started with 20 different event codes. So in 2018, when we started with Java, and then at the back end, it was using MapReduce. It was running fine, but till 2020, as we had seen a lot of different teams try to reach out to us for the similar data. So couple of millions that reached to couple of billions, and 20 event codes reached to 200 event codes. Now, since we had more data, so we had to process and we had to require a lot of compute information, and we needed that. So we have an on-prem cluster, 1,000 nodes on-prem cluster, which is a Cloudera distribution. So at that time, our management decided that we don't have to purchase more physical servers, and there were some network constraint as well, that we don't have to now put more focus on our physical environment. We have to move to the cloud. So that's how our journey started, that first we have to move this big system to cloud, and then we'll move other systems in our group to the cloud. So in 2021, we took a decision, and then 2022, we had a cloud release, and then in 2023, we have built a complete ecosystem, not related only to ingestion, other factors as well. So if I'll talk about at high level, our system processes around 50+ billion events in a day. This data is being used by 2,000+ users. 100+ teams are using this data. Mostly it is batch, 95% is batch only. And we have a single source of truth whosoever has to use this data, they comes to our platform, they use the different tables that we create, and we create around 1,000 plus different tables with this framework. This data is being used in product team for doing the different analytics on the product, that if they have put some feature, how that feature is performing. This data is being used to do the performance analysis, that if this particular app or a product is being used by millions of users, how this product is being used and how is that is performing. This data is being used by different marketing teams for their customer segmentation. Let's say somebody wants to target a paid user who has not used a product for last 30 days. So for using this data, they could create a custom segmentation on Google or Facebook, something like that. Similarly, this data is being used for creating a 360-degree view of a profile, which is being used by the various teams to improve the customer experience. This data is also being used for a lot of reporting purposes, where they carry that how we are growing in terms of how users we have, how many conversion that we have, how many users that we retain, how many engagement that we have. So this data is being used all across Adobe for like many purposes. So when we started, so in 2021 when we started, we knew that we came from couple of million to like couple of billion. So this system is gonna scale, and in maybe in coming years, we might be speaking of 100 plus billions, something like that. So scalability was a big factor that we had to consider, that we want a solution which should be based on distributed computing, which should be horizontal scalable, and scalable in terms of the existing event codes that we have, and moreover, system should able to adopt more and more new event codes as well. So, one major goal was that we had to reduce the latency and improve the performance. The existing system, which is running on-prem cluster on Hadoop, it had multiple hops where the data is reaching through multiple hops. So there was a delay, and the data when reaching to the product teams or the marketing teams, it had a delay. So once in a day, that job would run and process the data, and then that user will be able to use the data. And in terms of performances, since it was based on map reduce, so it was taking a lot of time. Since we were dealing with like billion records, so sometimes a job would take 7 hours, 8 hours. So that way, one goal was that we have to improve in terms of latency and performance. We wanted a solution which is cloud agnostic, so that right now, we have a solution on Azure. If we want to move it to AWS or GCP, we should have that one. So we shouldn't be doing a lot of changes in the application. So with small changes, we should be able to port that application. And from quality perspective, we wanted that since we are dealing with a lot of data, though, how we are making sure that data should complete on time. It should have a valid records. It should have a uniqueness. It should have accuracy. So all these factors were there while creating the applications, creating the design. And similarly, in terms of configuration and monitoring perspective, that if we want to onboard a new event or we want to do automation, that should be configurable. We don't have to change a lot of code for that. So these were some of the goals that we had to take care while designing the system. Now, this was an important point in terms of platform, like which platform would work and which platform we should choose. Since we were dealing with like massive amount of data, we were using Hadoop. So Spark was an obvious choice that we had to use Apache Spark for this massive kind of information or for processing. Now, for the Spark, now we wanted a unified analytic engine, not only the batch one, it should have a capability of streaming. And not only this one, it should have a capability of machine learning as well, so that a one platform should be able to satisfy. It's not like for machine learning, we have to opt another platform. For streaming, we have to opt another platform. And for batch, we have to opt another platform. Auto-scalable in terms of, we wanted a platform where when a job is running, so as per the load, as per the volume, it should scale up and down. It's not like a custom normal Hadoop job where I'm specifying a certain capacity and then job is taking that capacity. Automatically, if my volume is in terms of TBs, so then automatically more and more workers should spawn. If my volume is very less, then it should scale down. So that way, auto scalability feature should be there. And then again, ease of use. It should be very friendly. One can easily try to adopt that environment. It should be very friendly that anybody having not so technical background like data analysis or something, they should be able to use this platform. And it should be multi-language. Since we use Scala, we use Python, we use Java, we use SQL, so it should support all the languages. And in terms of like go to market, it should be very fast. We should have that kind of platform where if we have to productionize our code or if we have to collaborate, then it should be very easy. For all these things, so that one we chose the Databricks. So Databricks support all these features that we wanted. It's cloud agnostic. The same capability is available on Azure. The same capability is available on AWS. It's very friendly. UI is there. Notebooks are there, which is a great way to collaborate. You can try things. You can try quick POC and then try to productionize the code. It supports multi-language. Auto scalability feature is there. You configure like minimum and maximum capacity, and then with that minimum and maximum capacity, Databricks logic that consider all the data that you're running and then accordingly performs the action. And since like a lot of users, a lot of teams within our group, they are not very much advanced in Apache Spark. So we wanted a solution where you don't have to provide lot many configuration, you don't have to tune the job, you don't have to specify number of executors, number of configuration for each of the executors. So all these things we want that the framework should abstract that knowledge and it should give us the best, at least best shot. And then if one having any advanced knowledge, then they could configure the parameters and tune the parameters. So Darwin is the name of the framework that we built. So how we built it? First, it's a Spark-based application that we created. Now, Spark, we know that it's a distributed computing. When we launch a job, it runs divided into different tasks. Tasks run on different machines. We have that one. So on top of that, apart from that, we created a multi-threading application within Spark. So what we are doing is, instead, if I have to execute any job, if I have to create in data frames, or if I have to take some action, so one action by default would be executed. And if there are 1,000+ different stages are there or different jobs are there, that would be spawned. But what we did, on top of that, we created a multi-threading. So that means at a given point of time, I can, within my application, I can spawn 30, 40 different threads, and then it would spawn 30 different jobs on a Spark and would execute the job. We created a efficient data model where the scanning in terms of getting the new data or getting the incremental data should be very less. So we created a efficient partitioning strategies. We created a very common schema. So we create around 1,000+ tables. For that one, like we have two categories of table. One is the raw data that we get, the basic cleaning that we do in terms of removing the duplicates, removing the null value, taking care of that records are clean. And the second one is the max layer, where we create a lot of aggregation, we create a lot of UDFs. So for that one, we wanted a common schema so that within a framework, that common schema should be suffice and it should able to handle lot many tables at one go. So we had one column where we were getting JSON. So JSON was varying from one event code to different event code. For one event code, it was different data that we were getting. For one event code, we were getting different data, but other columns were there. So this became very easy for us to process this massive amount of information. Then there was a ask that we have to remove the duplicates in terms of the current data that we are processing on a run. Let's say we are processing 6 hours of data, 3-4 terabyte of data. If there are duplicates, we have to remove that one also. And then there was a thing, if there is a duplicate in last few days of data, we have to remove that as well. For that one, we chose an indexing based logic. Whatever the unique ID that we had, event ID. So for that one, we create a light index-based tables. So instead of looking and joining the actual heavy table and doing the shuffling, so we were having very light tables where we were looking for a historical data, having some duplicates and removing that one. And then we chose the delta format. Why we needed the delta format? Because our data also goes for the GDPR, where we have to remove certain records if somebody is doing the GDPR request. For that one, we had to choose a transaction model because we are dealing with massive data. If I have to update a single record out of billion, then and if my single partition has that billion record, so I would have to rewrite the complete partition because by default there is no way to change that one. So that's how we had to choose a delta format. And in delta format, apart from this GDPR, we are doing many optimization in delta format in terms of using optimize so that all the small files could be compacted into a bigger file. And in terms of joins, we were using Z order so that the similar co-location could be there and efficiently it can join the data. We have a lot of automation in terms of where if a new events come, automatically we onboard that one. And if the event is not inactive, so we had onboarded an event, but right now we are not getting the data, so automatically it will detect and it will remove the data. We had segregated the data into multiple categories. So we had to process around 500 different event codes. For that one, what we did, all the heavy one, we took it in one category and then provided the efficient configuration related to that one only, so that it should not be mixed with the event code which is having data in MBs and the other data which is having in terabyte. So we did that. And there are many event codes which are driven by SLAs, where those are very important, that a lot of teams are looking for those events and they need those events to process on time. For that one, we also created a different category where all the light and important event code could be processed separately. So we chose a strategy where based on volume, based on the SLA, where we clubbed different events and provided the efficient configuration in terms of shuffle partitions or other things so that efficiently we can process this massive amount of information. We had to process many things. So that way, we created a batch ID based off concept where each batch is unique and we can track that batch. We can process that batch so that there shouldn't be any case of data loss. We should be able to monitor that in particular batch, how many records were processed, how many hours of data was there. So that's how we brought the concept of unique batch ID, and that batch ID carries the complete information and it tracks from starting point to end point. Now, what it does at the back end, it has, since I've mentioned that Spark is there, threading is there, so each thread has to perform certain tasks. Like it will read the data, it will read the data, it will perform some cleanup, then it will remove the duplicates, and then it will write the data into multiple tables, and then it will commit the checkpoint. So thread is over. So similarly, multiple threads will do and keep on doing this work. And we kept the metadata very light. We are using MySQL for the light metadata, for maintaining the metadata, where in like handling all those scenarios where, let's say, a job has written the task, but my checkpointing has failed, where there is some problem in source, not able to start the thing. So a lot of failure scenario that has been handled through keeping the light metadata. So we check that one, the data has been processed or not, or correct checkpointing is there, all those scenarios. This is the technological landscape that we use. I'll quickly touch upon. So we use Spark for processing. We use Airflow for orchestration on cloud. We have a cluster on-prem where we use Uzi for the on-prem orchestration. We use MongoDB for collection of data quality stats and bit of streaming thing. We use multiple languages. We use different microservices and Databricks that we are using, Hive, all this technology, different landscape that we are using to process the information. So this is a very high level architecture. So first, our flow starts from here, where we have data on AWS, so on different buckets. So this is a Databricks environment where a one Spark application reads a data from S3 using S3 API so that different filters could be applied and you get the incremental data. And then it it basically it reads different event codes and it writes the data into a table, which is a Hive table, and storage is ADLS. Similarly, this one also does the same thing. So this process like 300 plus 50 events, and this process around 150 events, different event codes, and they are doing what? They at high level, they are just reading the buckets using the AWS SDK, and then there's a Spark application that reads from different bucket, create the files, create the different path, and writes the data into this ADLS location with some partitioning technique like event code and hours. And then this is the main application, which what it does is, so it reads from this location, and then as I have discussed, that it is a multi-threading application within Spark. So when we launch an application, let's say it's a 32 core machine or something, so then, for example, we are spawning 20 threads. So this 20 threads will at a time read these 20 events. So these 20 events are nothing but 20 different tables. Then they will process the information like removing the duplicates and doing the historical dedupe, ingesting the data, all those things. And then this is on cloud and this is on cloud. So as I mentioned that we had a system on-prem earlier. Right now we have stopped the compute on-prem, but there are few users who are still using the on-prem. For that one, we had to sync this massive amount of information on the on-prem as well. So for that one, we are using the DistCP, and how we are using the DistCP, since we have like 500 tables, so we can't have 500 different jobs to copy the data one job to another. So what we have done is through the base location, to base location we have mapped. So in one single DistCP job, we are able to transfer the data for based on different categories. So if one category is having 100 different event codes, so in one go we are able to sync that data for 100 different tables. And then again, since it is a Delta format, so Delta format is not supported in Cloudera, so we had to do some conversion at the back end and then we have a Spark job which converts and then finally write the data into this one. Now this was running fine, like we had this one, right? In 2020, the system went live. We were happy in a couple of weeks, and then on fine day, we started seeing some problems related to some performance, problems related to data quality. Some part of data quality we had handled, but some parts were, let's say there was some problem in the source. The data which was supposed to, let's say there is an event where we expect 50 millions event in one run, but due to some problem in source, out of 50 million, let's say we got 20 millions. So that was an issue. Downstream started creating this problem. Let's say there was a problem in the Airflow DAG due to some bug that they didn't trigger the job. So that didn't trigger the job. There was no job failure, but the data didn't reach on time. We are using ADLS storage account, and initially we were using one storage account. Since we are dealing with like billions of events, so storage account had a limit in terms of ingress or egress, that for particular this one you could have maybe 30,000 or 50,000 requests per second you can read or write. You have a limit of bandwidth of 10 Gbps or 20 Gbps that you can do this one. So we started getting quality issue. We started getting some errors in terms of, because that limit was breached from storage account perspective. We were getting some read issues or write issues, and similarly, when we went, so we were able to save around 60-70% compute when we moved from on-prem to cloud. But from cloud perspective, storage cost started shooting, because we were generating around 1 petabyte on a monthly basis, and compute was there because a lot of things were there, and so we had like couple of problems to solve. We had one, data quality, in terms of like how we ensure that the data is complete, how we can ensure that data is data is data is timely is there in terms of performance, how we can make sure that the storage account that we had, how we can resolve that one. So how we can optimize the compute cost, how we can optimize the storage cost. So these were the problems that we had to solve. So first was the data quality. Now in data quality, like we have a couple of parameters are there in terms of data quality. First is accuracy. Whatever the data that you are processing, it should be accurate. Whatever the source is there, the data that is generating from source, whosoever is reading from downstream, it should have the same set of data. It should not have bad records in terms of malformed JSON or corrupt. So that should not be there. Timeliness, whenever we are supposed to, let's say somebody is waiting at 2 p.m. that when the 2 p.m. job would finish, and then they would start reading this data for their machine learning problems or for reporting. So that data should be able to refresh at that particular time. Completeness, whatever you are processing, whatever is expected, so that should have a completeness in terms of the volume that users are expected, that this is the volume that we're expecting. Uniqueness, it should remove the duplicates. It shouldn't have that historical and self-dedupe. Consistency, like a single source of truth should be there. So few things we were able to solve in our application, like uniqueness, we already solved. Consistency, since that was a single source of truth, that was already there. Accuracy we were maintaining at high level because we were making sure the bad records need to filter out, and certain UDIFs were there. They need to make sure, they were making sure that the time format or a different time zones or a naming convention should be taken care. But the problem was timeliness and completeness. So timeliness is how we are making sure the job is getting completed there, and completeness is how we are making sure, because since we were processing a lot of jobs, so it was not manually possible to check each and every job that it was supposed to get 30 million, but right now it has processed only 50 million. So we had to come up with something that it should be automatically, process that one. So we came up with, data quality framework, which we created to handle this scenario. So what we did at high level, we have a, compute so we have a this metadata where we create some rules based on, let's say I have a table, I just want to do count star for this table, or I have a advanced rule where based on country code or a product, I want that different counts. And then my compute service will read the data and execute that one. And then again, there would be two levels. First is normal alerting. My count is not matching, alert would be generated, some problem. But normal query was not there. So we have, let's say we want to check the completed in terms of anomaly detection. Anomaly detection, where the trend was every day it was 15 million, 15, 16, 15, 16, but suddenly I got it 50 million. Or I got it 5 million, 10 million. So anomaly, my ML model should be able to detect whatever the run that you had. It should have the correct lower and upper limit or not. Otherwise, it would generate the problem. So we had ML service where using the anomaly detection, we have come up with 1 or 2 algorithm where we have trained the model on the previous data where we have some counts, their upper limit and lower limit. And then accordingly, we are basically able to guess whether my job is running fine or not. And then alert manager is able to come up with the right notification that this job is not working fine, or data was not complete, or this job did not get complete. Let's say job was not able to run due to some error or something. So that way even we would get a count 0. So as the moment we'll get count 0, we'll come to know there is some problem in the, there is upstream, or there is some problem from our side. So we are able to rectify that one. Now, so data quality problem we had solved. Now was the compute. Though we had optimized in terms of using the Spark, doing the aggregation in terms of choosing the category, provided the best configuration, but still there was a scope. So in Databricks, from database perspective, like what we do, we use the job cluster. So there is a difference between job cluster and the general purpose cluster. Job cluster is, first of all, it costs half the price from the this one, and when the job would get finished, automatically the cluster will tear down. The second thing was we are using the auto scaling automatically. We are just providing the configuration, and then from configuration, based on the volume, it is scaling up or scaling down. We are maintaining a pool. Pool is a set of ready nodes. It becomes very handy and efficient. If the pool is there, automatically when the cluster is demanding new machines or scaling up, automatically machine would be there and it will be very easy to start. Then it will reduce the cost. And we were using the automatic termination. We also use Adobe cluster for some analysis. For that one, if the cluster is not active for 10 minutes or 15 minutes, automatically it will tear down. From Azure perspective, so initially we were using only on-demand instances. So on-demand instances, and then we've started using the spot instances. Spot instances are 30%, 40% cheaper than the on-demand instances. But the downside is, in case Azure can taken back those machines. So there is a problem that if the job is running and somebody has taken the machine could go down. For that one, we were taking the best combination. For driver, we were using the on-demand, and for workers, we were using a spot instance. And for that one, we had a policy if the spot instances is not there, it should fall back on-demand. Now, this were the basic thing. From application perspective, we had already done some. Efficiency in terms of data model or avoid shuffling, grouping. There was a scope. Can we use machine learning model to improve or to save our compute? Can we do that one? Yes. So we did that one. So how did we? Because Databricks was efficient, but Databricks had some problems with respect to our use cases. So Databricks, how it works is, let's say my job is running, and then Databricks thinks that now my worker size right now is 5, but it should scale up to 50. So it'll spawn the machine. It'll take 5 to 10 minutes, and then bring all the machine. And then let's say you are running with 500 machines at a time, and Databricks algo thinks right now you don't need 500 machines. You need only, let's say, 300. So it'll scale down. So all the machine will tear down. And then next moment, again, it feels that 300 to 500 should go. So all this will go. So when the machine is going up or going down or requiring, that cost is, we have to bear the cost. So we thought, can we do something in terms of machine learning? Can we predict what should be our compute? Can we predict if I provide this compute, then what should be my SLA? So for that one, what we did, the basic thing, so when we use Spark provides certain matrices in terms of like how many jobs it has created, how many stages it has created, how many tasks it has created, and for each of the tasks, what was my time, for each of the tasks, what was my read and write, everything was there. So if you go to a Spark UI, you get that information. We wanted to use that information. For that one, what we did, so again, for that one, we created a framework, but basic idea was we place a Spark listener in our application, and whatever the different alerts or the different matrices Spark was generating internally, we capture all those matrices while running the job. So by end of the job, we had all those matrices, that how much time it took, how many stages it launched, how many jobs it launched, what was the time taken, everything. For that one, then we built our model on top of that to predict a time. So we use a random forest regressor for that one, and we were able to, by couple of cycles, we were able to predict that for this one, this is the right configuration. For this job, this is the right configuration. And if I want to meet the SLA, this should be the best information. So at high level, I'll cover the architecture. In this talk, I have covered a couple of architectures. So I'm just high level I'm covering. But if anybody wants to go deep and wants to understand more, they could connect me after this session. So this is, we call it Unified Cost Analyzer. So this is a framework that we created. But what I was talking, the basic idea was, whatever the job is running, within that job, just place a Spark listener and get all the matrices. So once you get all the matrices, and then we place that matrices into a table, and then there is a job which basically clean the stuff, do some cost calculation, and put the metadata. in MySQL, and then there is a there is a ML model which runs on this model and predict that one, and then it forecasts in terms of what should be the job, what should be the what should be the right configuration in terms of number of workers, what should be the right configuration in terms of VM family, all these details it provides that one. So we use how it works. So we spawn our jobs through Airflow. Airflow spawns the jobs on Databricks. Databricks, we have a listener, and then once the job would over, then it will create a data on table, and then we fetch this data and do some enrichment in terms of cleaning the data, preparing the data. Finally, we push the data to MySQL. This module will pick the data and finally able to predict the model. Now we had solved the compute problem. Storage problem was there. Storage, as I mentioned, that there was a problem in terms of when we were using only one storage account, we were hitting the limit and we were getting ingress and egress issue. For that one, what we did, instead of creating one storage account, we created 3 different storage accounts. One was for the landing layer, where we had a system, we were reading the raw data. Second account we created for the curated layer, where we were removing the duplicates and doing some basic cleanup. And the final layer, the presentation layer, we were doing the aggregation and applying the UDF. So this is how we were able to solve the storage problem. And then there was a problem in terms of size. Every month we were generating 1 petabyte information, because by default, when we go with a Z standard, when we go with Delta format, it uses internally the snappy compression. So it uses snappy compression, and since and we moved from ORC to Delta, so automatically 30%, 35% our size went up. So we had to think that how we can compress the data, because our annual cost of keeping the data was more than the compute that we use, because we were using 1 petabyte monthly, and then we had 20 petabyte historical. So automatically it was costing around $3 million+ on a storage perspective. And then we started that we have to evaluate, and then we need to come up with that which compression technique we use. And first we have to apply on incremental data. The new job would run, that will run on a new compression technique. And finally, we would have to use the historical compression, the data that we have around 20 petabyte, how we are going to compress the data. And the DLM. DLM is the data cycle life management, where how we are making sure that if the data is not used, why to put in a hot tier? Why can't we put in a cold tier? Cold tier is around 40% cost less than the hot tier. So we had created a policy where all the last 6 months data we put it in a hot tier, and rest data we move to the cold tier. When we did some comparison in terms of compression, so by default it uses a snappy. So we had 2 choices, ZZip and Z standard. When we did the ZZip one, we could see that 30% the size reduction as compared to snappy, and 32% when we use with Z standard. When we had a write or read one, we saw that write was 20% heavy on ZZip, but in case of Z standard, it was taking only 1 to 1.5%. Similarly, for read time, we could see it was way much better performing than the original snappy. So the clear winner was Z standard, because we already had a lot of adoption in the industry in terms of Facebook, Uber, or Amazon. So all were saying that this, and we could also see from when we did, when we applied this one. So as you can see, the number of records were same. The data size is going down, bytes per record and size in TB. So this is how we got the confidence by applying the incremental compression, that if we would apply this one, we would have at least 30 to 35% saving in terms of storage. So we applied that one. And when we applied this compute, when we applied this storage in terms of the Z standard compression, incremental and historical, and compute saving in terms of using the best technique of the mixture of spot instances and on-demand instances, plus using the machine learning to predict that instead of using this configuration, just apply this configuration, we were able to reduce around 400K for compute, and for storage, we were able to reduce 1.5 million. So out of 1.5 million, we were able to save around 1.2 million from reducing only by applying the compression using the Z standard format, where the original data size, the historical data size we had around 22 petabyte, that got reduced to around 11 to 12 petabyte. So we had huge saving in terms of this one. Now, this was the overall journey that we had. First, we had a problem that we had to process this information. We came up with the ingestion framework, which was able to solve, it was able to scale and process able to billions of events in a day. But then we came up with certain problem in terms of performances, in terms of the storage account that we had limited. So we had to scale that, and we had to create multiple storage account, and then had to create multiple views so that the all the downstream user doesn't have to do something from their side. Then we had a issue related to data quality. Most of the issues we had already handled in application, but there were some issues which could not handle in application, and there was a scope where through machine learning, we were able to solve this problem. So we came up with the data quality framework, and applying the different rules, we were able now we are able to predict the error. Now we are able to see if there is any anomaly detection, if the data is complete, if the job is running, or if the job is not running due to any bug in the system of the external things that we use to process the information. When we moved to the compute, we had basically use the best practices in terms of Databricks, best practice in terms of Azure. But there was a, when we actually studied the Databricks auto-scaling algorithm, we came to know there is still a scope where by using ML, we could still do the reduce the cost. So by leveraging Spark's framework itself, which captures all the matrices, we place that listener in our application, got all the matrices, placed into the, and filter it, clean it as per our requirement, then give it to the ML model by tuning that model. And now this ML model, we also use the ML flow of Databricks to scale, run that model in terms of tracking, in terms of deployment, in terms of running the different experiment, using the feature store. So we are using the ML flow feature of Databricks for doing end-to-end automation. And then we had a pain in terms of storage, where due to this snappy one, the data size got up, where the even the storage was taking more than the compute. And so we had an opportunity to squeeze the one. We had evaluated a couple of compression algorithm. We came up with Z standard is at par with the existing one. So we came up, we applied on incremental, then we applied on historical one. And on top of that, we applied the DLM policies, where the data which was not relevant or nobody's using, and through some tracking, we moved that data to a cool tier. Now, anybody having any question or something I would like to answer?
Hi, thank you for the presentation. I'm in awe for the complexity. I missed the beginning. Could you please tell how did you convince the stakeholders, the business, to invest in such technical project that, optimize this, optimize the state of your system? Could you share that? Because from my experience, this is a very tricky thing, always to convince people to invest in those kind of initiatives. So I would be curious to learn more.
Yeah, it's a great question. First of all, in terms of technologies that we didn't have to convince too much stakeholders. So in terms of it came from the business. They wanted this data. So they wanted this data to run the different models, to predict, to improve the customer experience, to improve the personalization, to do the segmentation. So they needed this data. And the problem was the data was growing with the passage of time. And for two reasons, users are, Adobe is growing. Plus, we were capturing different events. We started with few, and then we captured another one. This is how. So the problem was clear that everybody needs the data. We cannot escape the data. We have to process that information. The tricky thing was when we were moving from on-prem to cloud, then we had to take a lot of decisions. We had to involve certain stakeholders, like still moving from here to there. Then how we would convince everybody that go and start using the cloud. Now we are not gonna process everything on-prem. So that was a tricky thing where we had to convince, we had to, we had certain meetings with a lot of stakeholders that this is a problem, and now onwards we are going to process data on cloud. And then internal problems were our problems that we have to save compute. We have to make sure the data that we provide to different teams, it should have quality in terms of everything that I covered. And on the other hand, providing quality and processing this massive information, we also have to be very mindful in terms of cost. And how we had internal targets that this was the cost, we have to reduce this thing. Then we sat, we explored little thing, we failed, and then finally we came up with a refined version. And still we are evolving. It's not like end of the story. Now we are coming up other things that we have to evolve as a system. But it took us a lot of time to be here in terms of learning, in terms of different failures that we had, and the different technology that we tried, and a lot of performances that we tried. So all this thing took us a lot of time.
First of all, thank you for your speech. And my question is like, why did you think, actually, what led you to think that storing the data in the cloud will be far more better than having your own server? And actually, if you can tell again, what are the advantages you got?
So basically, if I have understood your question correctly, you are saying why we are now syncing from cloud to on-prem, right?
I am asking like, you can store the data in cloud?
Yes, we
or
are.
in your server, yes? Or on your servers?
So basically, we are using the cloud storage. We are not using our server.
From beginning?
Not from beginning. When we moved to the cloud.
Yes, but before moving to the cloud,
we were have that storage in the form of HDFS. We had that, so we were having that storage in HDFS.
Yes.
But since like us that we grew within our groups, all other teams also started growing and started seeing a lot of data. When we started, we started with like 1,000 nodes, and it was like 30% capacity was used. But by 2020, it was 85%. Everybody needed compute, everybody needed storage. So that's how the one thing was, either we could maybe bring more server, 1,000 to 1,500 or 2,000. Then we thought that again we might hit a problem, and moreover there were some networking challenges as well, that we might scale up the compute, but maybe there are some parts of networking we might not be able to scale that network within the cluster environment. So we might face bottleneck. For that one, we had to move to the cloud, and for that one we chose ADLS as a storage.
Yes. Okay. Thank you very much for your explanation.
Hi, Rocky. Great presentation, firstly. So just one basic question, like why not AWS, why Azure? So I could understand and relate to your architecture and everything, like everything can be done on AWS with a lesser cost at some features, right? So why did you decide Azure?
So basically, I would say that yes, the same framework and same offering as I mentioned, that cloud agnostic, Databricks, AWS is very much supported on Databricks, but it was an internal decision because Adobe has an, I think, partnership with Microsoft. Though that was the main reason, and moreover, some sources are already there were on Azure. So that was more of a, I would say, stakeholder decision. It was not related to any technology or challenging, but we kept it open. Now we are going forward in that way, where we might put this application on AWS as well, so that whosoever is on AWS, because our sources are already there on AWS, so they could start in getting the data. But since most of the teams were already there on Azure, and plus like some partnership was already there, so that was a key stakeholder decision, not something related or some constraint related to that.
Okay, nothing technical. It was
nothing
more,
technical, and we kept it very open. Like Databricks is there, the day that we want, we can move. We just have to do some little bit configuration, we'll be able to put that application there.
Makes sense. Thank you.
Hi, great presentation. So one question related to the data locality, right? Specifically when you're migrating from on-prem to on-cloud, right? Movement of data becomes a challenge, and specifically when you're talking about petabytes of data where your system was already generating that, right? So if you can just quickly walk us through that process of, what was the idea behind, this migration process? Because that's really, really critical, right?
So first thing was I mentioned that we needed more compute.
Correct.
That was the main bottleneck. We wanted that we have to process, we wanted compute. For that compute, we wanted a physical servers, and then there was a constraint that we don't have to add now more physical servers. Correct. So that first point was we have to go to the cloud. Second was how we are able to like move the data, how we can move the data, right? So for that one, initially it was challenging. We used the data box option. So we didn't transfer the data through network.
Right.
We opted a physical, like Microsoft offers a data box option where
Correct.
we selectively chose and 5 petabyte of information we put it, and then within a month we were able to do that. And then we had a strategy that both systems were running fine, were running parallelly for a couple of time. Like it's not like we shut down the system on-prem. It was running fine, but we started that system on cloud as well. And then the historical data, we put it from here and back from data box option, we place it there, and then we loaded the history. Then we had this history loaded, then we shut down the compute here and simply transfer the data from here. Compute was over. Did I answer your question?
Yeah, you did. Thank you.
Okay. Anybody having any other question? Okay, thank you so much.